Hello and welcome to the solutions videos for Unit 3, Lesson 1, Scott's March Motivation. So the ready section says, for each problem, place the appropriate inequality symbol between the two expressions to make the statement true. So the first one, we're told A is greater than B, and then we see that both A and B have been multiplied by 3. So A is going to remain greater than 3A is going to be greater than 3B, since when we multiply both by 3, both their quantities increase by a multiple of 3. Okay, so here, A is greater than B, and we see B minus A, and we say A minus B. So those are actually going to have the same difference with opposite signs. Right, so B minus A, since B is a smaller value than A, when we subtract B minus A, we're going to get a negative value here. Whether they're both negative or one's negative and positive, as long as B is smaller than A, those are going to produce a negative value. Here, we're going to get a positive value since we're taking a larger number and subtracting a smaller number. So the difference will actually be, the absolute value of the difference will be the same, but this A minus B will end up positive, and a positive is going to be greater than a negative. Okay, here again we have A is greater than B still. We see that we've added a constant value onto them. So we're adding a constant value. A is going to remain, A plus X is going to remain bigger than B plus X. Okay, here it tells us X is greater than 10. Now that's actually really important information because these grow at different rates, right? They actually intersect at two places. So if I just want to do a quick sketch, I'll do, let's do 2 to the x first. So the initial value is 1. And when I have x is 1, well, 2 to the first is 2. So let's say 1, 2. When x is 2, 2 squared is 4. So that's going to be one of the places they intersect. And I'm going to kind of just make this 3, 4. So here we're doubling every single time. So let's say that 8 is about there. In 16, this is not to scale, 16, 416. There we go. So I might just fix these a little to make it a little bit more exponential looking. Let's say that's 3, 8. And then it does have this part here, but we only care when it's greater than 10. So none of these values are greater than 10, but it's going to be helpful, I think, to visually see what these graphs look like. So x squared, so that's our quadratic. So we have 0, 0, 1, 1, 2, 4. So there's an intersecting point right there, 2, 4, 3, 9. So actually when we get 3, this is a little bit faster. Right? 3, 9 is just slightly higher. And 4, 16 is actually going to be the same thing. 4 squared is 16. So this graph, now my hand drawing is really bad. Yeah, it's a really bad hand drawing. But I can see that there's at different points, like here exponential is a little bit faster. And then our exponential is going to become faster again too. So as x increases, this grows faster. But there's this little segment in between that our quadratic is faster. Now my drawing doesn't make it look like it, but we can see right here that at that 3, 9, the quadratic has a higher output value. So this one is actually faster in between that interval. But we only care about x as being greater than 10, and since our exponential grows much faster as we get larger and larger and larger, bigger values of x, that one is going to be the greater value. All right, question 5. Very similar. I think visually it's nice to sort of see these again, but we already have our quadratic graph up there. I'll kind of re-sketch it down here. So here's our x squared graph, y equals x squared. I'm going to highlight this point 1, 1, because the square root of 1 is also 1, so that's actually going to exist on both graphs. But when we have a square root graph, when our values are less than 1, we actually have that upward curve, right? So there's our square root of x, and here's our y equals x squared. So it is that y equals the square root of x is faster until 1, but anything after that x value of 1, our x squared graph is going to produce much greater values. Okay, so again, x is greater than 10. We have x squared and x cubed. X cubed is going to grow substantially faster than x squared, so that's going to be the larger value. Okay, and let's go down to problem 7. So here we're actually now looking at values between 0 and 1. So this makes the big difference. So we have y equals x, or just x and x squared. But I'm going to graph y equals x. So y equals x. And we have 0, 0. And I'm going to put 1, 1 right there. Just a quick sketch. So x squared also has that property, but we curve down before we get to that 1, 1. So anything between 0 and 1, this is actually less. That x squared graph is less. So the greater value is y equals x, or x is going to be greater than x squared between 0 and 1. Okay. The square root and just plain x. So this is actually another very similar one. We already kind of showed the graph of the square root. Ooh, let me fix that. We got a little... Okay. We already showed that graph. Hold on. All right, there we go. But I'll sketch it again quickly. Our square root graph has sort of that curve. We have that 0, 0 point, and then the square root of 1 is 1. Well, we have those same points for our y equals x graph, but that one's linear. So notice it's less than it. This one is underneath. So between 0 and 1, the square root is larger. Okay. So number 9, if x is between 0 and 1, again, we're going to actually have this one be our bigger value. If we want to stick with our visuals, y equals x. I'll just show the top half of it. Well, I'll draw the whole thing. So 1, 1, 0, 0. Now 1 over x also has this point 1, 1. So 1 over x, let me switch my color up a little bit, has a vertical and a horizontal asymptote at 0, 0. So at y equals 0 and x equals 0. So that has that shape, and it exists down over here too, but we're only looking at this positive range, so I don't need to focus on that. But we notice that in between this area here, right, in between 0 and 1, our graph for our exponential, for 1 over x is approaching infinity. So this is approaching positive infinity. So that's going to be much, much larger. Once we get to whole numbers of x there, like 1, 2, 3, then that becomes smaller because they approach 0 on this side. But right there, we're approaching infinity. Okay, let's go to our set problems. So it says for problems 10 through 12, the recursive rule for a polynomial function is given in the form of f of n equals f of n minus 1 plus our rate of change. So the first thing it wants us to do is use the recursive rule to fill in the first 5 values of the function in the table of values. It wants us to identify the rate of change, classify the type of polynomial as linear, quadratic, or cubic, and use the difference in the table to check your answer. So, rate of change. Well, it tells us that the rate of change is this value added at the end, so our rate of change is 7. Since that's a constant rate of change, this is going to be a linear polynomial. So, the next part, fill in our table, right? Well, it tells us that f of 1 is 10. Now, our table is all the way down here. F of 1 is 10. So there's a few ways. Since we know it's linear, I could just go ahead and keep adding 7 to this. So I get 17, 17 plus 7. So I could do that, but I could also use my formula. So let's practice that. We know it's f of n minus 1 plus 7. So if I want f of 2, which we know is now 17. Well, f of n minus 1, 2 minus 1 is 1. So it's going to be the value for f of 1 plus 7. Well, the value for f of 1 was 10. So 10 plus 7 is 17. So if I wanted to find f of 3, well, f of 3 minus 1 plus 7 becomes f of 2 plus 7. Well, we just said f of 2 is 17, so 17 plus 7. So we're getting that same results with just a different way of thinking it. So for linear ones, we don't need to plug into the formula every single time once we can predict the pattern. So 17 plus 7 is 24. 24 plus 7 is 31. And 31 plus 7 is 38. Okay. Let's go down to problem 11. Oh, wait, we wanted to check. Use the difference in the table to check your answer. So that's kind of what I was actually doing the first time. So I guess we'll kind of use the formula to check our answer instead, since I used the table difference to get our answer. So f of 4 minus 1 plus 7. Well, that gives me what f of 3 is, plus 7. Well, f of 3 was 24 plus 7, which is 31. And lastly, f of 5. So 5 minus 1 gives us the 4. So f of 4 plus 7. Well, we just said f of 4 is 31. And 31 plus 7 is 38. So there we have those same values that we see if we just added 7 from our table. Okay, question 11. The rate of change is 2n here. So because there's that n here, this is a quadratic. Quadratic. The second difference is constant. Right? So we have that first term tells us f of 1 is negative 3. So we'll follow the directions on this one now. So if I want to find f of 2, I do 2 minus 1 plus 2 times 2. Right? I'm plugging in that n value, which we said is 2. So 2 minus 1 is f of 1 plus 4. Well, f of 1 is negative 3, so negative 3 plus 4 is 1. So we get 1. Okay, let's go to f of 3. I'll start skipping space a little bit here. 3 minus, remember we're always going to do, and I'll write the formula above just in case we forget. Oh no, it's right here. So 3 minus 1 is going to be f of 2 plus 2 times whatever we plugged in here. That's our n value, so 2 times 3. So this becomes, well, f of 2 we said is 1. 2 times 3 is 6, so we get 7. All right, f of 4. So 4 minus 1, this means we're going to use the term f of 3 plus 2 times 4. So we end up with 7, because that's what f of 3 is equal to, plus 8, which is 15. Okay. And then lastly, f of 5. Well, f of 5 minus 1 is the same thing as f of 4 plus 2 times 5. So f of 4 is 15. 2 times 5 is 10. So I end up with 25. So we have our table values. Now let's check that that second difference is constant. So the difference between negative 3 and 1 is 4. The difference between 1 and 7 is 6. 7 and 15 have a difference of 8. And 15 and 25 have a difference of 10. So if I look at these, those all have that constant difference where I'm adding 2 to get to the next one. So that second difference is constant. That's wonderful. It just is reassuring that we did get the same second difference. Okay, number 12. So it tells us that our leading term is 1. We see this n squared here. So our rate of change is n squared plus 3, which means it's cubic. right? The third difference is constant. So the third difference in constants, we see n squared, so cubic. So let's go down to our table here. I'm just going to rewrite our information so we don't have to scroll back up. Plus n squared plus 3. All right, so that's sitting at the top for us. So f of 1 is 1. So let's find our f of 2. I'm going to give us a little space to our check. So f of 2, well, 2 minus 1 means we're going to use our value from f of 1. 2 squared plus 3. So instead of n, I'm going to write 2 squared plus 3. So our value for f of 1 was 1. 1 plus 4 plus 3. That gives us 1 plus 7, or 8. F of 3. So this time, 3 minus 1, we're going to use the value for f of 2 we just got. Now we're doing 3 squared plus 3. Right, so that gives us 8 plus, well, 3 squared is 9 plus 3. So 9 plus 3 is 12. So we have a total value of 20 there. F of 4. So we're going to use our value from the term before, f of 3, plus 4 squared plus 3. So our value of f of 3 was 20, plus 4 squared is 16, plus 3. So we get 20 plus 19, or 39. And lastly, f of 5. So we're going to use our value from f of 4, and then we're going to do 5 squared plus 3 as our rate of change. So our value for f of 4 was 39. And we're going to add 25 plus 3, or 28. And I don't have quite enough room there. So 39 plus 28 gives us 67. Good. Okay, so now we have all the tables. Let's check it. So the first difference we see here is 7. And then we have a first difference of 12. Here we have a difference of 19. And here we have a difference of 20. Wait, where's my mental math here? 67 minus 39. It's 28. What am I doing? Okay, I had to think a little bit about that one. Okay, so we can see that there's not really a constant difference here. The difference between these two numbers, 12 minus 7, is 5. And here, 19 minus 12 is 7. And here, 28 minus 19 is going to give us 9. So that's where, here we're at our second difference, and that's where we see some constant things here. There's the constantly adding 2 there, but it did take us that second difference to get there, which confirms this is in fact cubic. Okay, so that's it for problem 12. So let's go down to problem 13. So 13 is a little different. It gives us the table this time. So it says find the rate of change for each table of values. So that's the first thing we want to do. Write the recursive form of each function. If the rate of change is constant, write in the constant value. If the rate of change is a function, write the equation of the function that describes the rate of change. Identify the type of function. So we're basically going to do the reverse of what we were just doing. This time it gives us the table. We're going to find the information. So let's start with looking at our differences here. Here the difference between 6 and 6 to 7, we have to add 1. Here we add 2. 9 to 12, we add 3. 12 to 16, we add 4. And then lastly, we add 5. So there's definitely some pattern here, right? We're seeing that 1, 2, 3, 4. So we're certainly not linear because it's not going up the same amount every time. So let's look at this second difference, right? This second difference is constant. 1 to 2 is 1. 2 to 3 is 1. 3 to 4 is 1. and 4 to 5 is 1. So this is definitely going to be a quadratic. So it's a quadratic that we're dealing with. I'll fill that in first, right? Quadratic. Now, our first recursive rule, let's kind of do that first. F of 1, we know, is 7. And we don't have to actually start. We could actually start with the 0. So I'm going to do that since that's the first term. I just wanted to show you that we do know that f of 1, and we were using that in the problems before. But f of 0 can be our first term. So then our rule would be n, f of n. We still want to do n minus 1, right? So when I plug in, let's say when I do f of 1, I know that that result is going to be 7. So I want to think, okay, it's the term before it, so f of 0, so 6 plus something. Well, this one has to be 1. So this is just going to be a plain n here. So plus n. So that's one way we can think of it, and that's just an example of showing why we can use 0 first, right? If I had done f of 2 instead, well, that means I'd be using my term for f of 1. Well, f of 1 is 7. Well, I plugged in 2 here, so I add 2, which gives me 9, which is our f of 2 term. So here we're good. Our rate of change is n, because it's a constant difference of just 1 right there. So n, or 1n if you prefer. You can always throw the 1 in front as a little placeholder. That's never a bad idea. Okay, let's go to problem 14. So problem 14, here we are subtracting 5. Subtracting 5 again, subtracting 5 again, subtracting 5, subtracting 5. So our first difference is constant. It's a constant -5, which means this is a linear function, right? So let's start with f of 1 equals 6, because that's the first term they gave us. So every term after that, so f of n is going to be f of n minus 1 plus -5, or I'll just write -5 here. You can do plus -5 if you, and that one's linear, so that's it. Okay, let's look at our next one. So here we have a difference of +3, and then we grow to 5, then 7, then 9. So we can see that these aren't constant. However, they all have another constant after. They're all that addition of 2, which makes this quadratic. So we're going to have a 2n for sure, but let's be careful. Let's test this out so I know, so we're not quite done here. So f of 1 is 3. So that means f of n is going to equal f of n minus 1 plus 2n. Let's see if we have to add to this, right? So let's test this out. I honestly think when we have a table, this is one of the fastest ways we can go about it. So if I use my f of 2, that means it's going to be f of 1 plus 2n. And we want to decide, are we adding anything else or subtracting anything else to the n? Well, we know that f of 2 is 6, and f of 1 is 3. So 2 times 2, because that's what our n value is. This would give me a value of 3 plus 4, which is 7. 7 does not equal 6, so it means I actually have to subtract 1 to get this to be 3 plus 3, which equals 6. So my rate of change is 2n minus 1. So I want to include that minus 1 after. And that one is all set. We checked it. Let's move on. Ooh, hold on. Grab my screen on accident. There we go. So question 16. So here our first difference is adding 4, then 5 to 14, that's a difference of 9. 14 to 30 is a difference of 16. This is a difference of 25, so definitely not linear here. Let's look at these difference here. 4 to 9 is a difference of 5. 9 to 16 is a difference of 7. And then 16 to 25, that's a difference of 9. So finally, after doing this twice, that third difference is the same. So this means this is a cubic function. So we're definitely going to have an n squared. Now let's look a little deeper with that n squared. We want to see if we have to multiply that n squared or by anything or subtract. So let's just test out our rule first. F of 1 is 1. So f of n equals f of n minus 1 plus n squared. And let's just see if we want to add or do anything else. So let's test f of 2 out. So f of 2 is going to have to be equal to f of 1 plus n squared plus something, right? So f of 2 we know is 5. F of 1 is 1. 2 squared is 4. Well, 1 plus 4, that already gives us our 5. We don't actually have to add anything onto our rate of change. It is all set as just an n squared. So we are good. And if you want to test another one, go ahead. Let's test f of 4. So this should be f of 4 is 30. And we should have the term before 4 is f of 3. So that is 14 plus 4 squared plus 16. So does 30 equal 14 plus 16? Yes, it does. So our formula is correct. A nice way to check our work. All right, let's move on. So our go section is dealing with finding quotient. So find the quotient without using a calculator. If you have a remainder, write the remainder as a whole number. And it gives us an example of how it wants our answer to look. So let's look at this first one. 30 doesn't go into 5, so let's go to our second decimal place, or our second digit there. So 30 goes into 51 one time. 30 times 1 is 30. So if I subtract those, I get 21. I'm going to pull my 0 down. 30 goes into 210. Well, let's think of 3 and 21. That goes in 7 times. So 3 times 7 is 21. So 7 times 30 is 210. We're left with no remainder. So our answer is just 17. So question 18 says, is 30 a factor of 510? How do we know? Yes, since there was no remainder. Okay, let's move on to 19. So 19 says find 3,405 divided by 17. So 17 goes into 34 perfectly twice. So 34 or 17 times 2 is 34. So I'm going to subtract that, which gives me a 0. So I got to pull down my first term. 17 does not go into 0 at all, so I put a placeholder, pull down that second term. 17 does not go into 5 at all. There's nothing else to pull down, so that's my remainder right there. So remainder 5. So 200 with a remainder of 5. So question 20 says, is 17 a factor? No, since there was a remainder of 5. Okay, let's go on to 21. 21 wants us to do 3,405 divided by 92. So we might not be able to think of multiples of 92 as easily. It doesn't go into 34. 32 is too small. So let's look at 340. 92 is pretty close to 100. And 100 times 3 would be 300. So let's try 92 times 3. So 2 times 3 is 6. 9 times 3 is 27. Right, so 276. Now let's just, say, well, what if we tried it times 4? Well, here we get 8. 9 times 4 is 36. 3, so that's too big. So too big. So I don't want to use that. We're going to use 3. So we're going to use 276. We're going to subtract. So I have to start from the right side. So I've got to borrow from this 4. So 10 minus 6 is 4. Now I have 3 minus 7. That doesn't work, so I borrow from this 3. So 13 minus 7 is 6. So then 2 minus 2, I'm just left with 64. 92 doesn't go into 64, so let's bring this 5 down. Similarly, I'm going to use 100. So if I'm thinking, okay, 100 times 6 would be 600, but this is almost 650, right? So let's try 92, not times 6, but let's try it times 7. So 2 times 7 is 14, so I'm going to carry that 1. 9 times 7 is 63, plus 1 is 64. So nice, we're nice and close here. So we can use that number. I don't need to check anything else when it's that close. So that's when we multiplied by 7. Don't forget to put that 7 up top. So here we get 1 as the sole remainder. Well, there's nothing else to pull down. 92 certainly can't go into 1, so that means we have a remainder of 1. So question 22 says, is 92 a factor? No, since there was a remainder of 1. Okay, and that's it. That's all the problems. So hopefully you found this video helpful, and thank you for watching.